Okay, look at this. A massive number of students get the bus topology completely wrong on their exams, and honestly, it quietly costs them the grade. They just assume that because computers are physically lined up in a row on a desk, boom, that makes it a bus topology. Well, let me stop you right there. If you look at the red X on the left, you'll see the wrong way is focusing purely on the physical layout. The correct way, which we've marked in green, is recognizing that a bus topology is actually when devices logically share a single common communication link. I wanted to show you this massive exam trap right out of the gate so you can truly understand the mechanism behind the answer before you make this mistake yourself. Welcome to this immersive explainer. Today, we are diving into a masterclass on Cambridge IGCSE Computer Science 0478. Think of this as an inside-out digital journey. We're going to start deep inside the computer's physical hardware, expand all the way out to the global internet, and finally dive right into pure programming logic. Let's get into it. Section 1. The primary memory trap, navigating inside the hardware. So, before a device can connect to any network or even run a single line of code, it has to wake up. This is where the foundation of your computing knowledge really begins. And frankly, it's where a lot of easy marks are dropped. If you don't know exactly how a device boots up, the rest of the system just isn't going to make sense. Notice the clear, functional contrast between RAM and ROM here during that crucial startup sequence. Look at the dark blue section, ROM, or read-only memory. This is your permanent foundation. It's completely non-volatile, which basically means it never forgets its data, even if you pull the plug. It safely stores the BIOS, that vital firmware that literally wakes the computer up. On the flip side, we have RAM, random access memory. You can think of RAM as a temporary, super fast-paced workspace for your operating system and the apps you're using right now. But it's volatile. It forgets absolutely everything the second the power drops. So the crucial takeaway here is this. When an exam asks you to identify the memory used for startup routines, the only correct answer is ROM. Please do not fall into the trap of just writing primary memory. You've got to be specific. Okay, so our computer is awake and its operating system is happily loaded into RAM. Now it wants to talk to the outside world. But before we expand our view from that internal hardware outward to the local network, we really need to nail down a core vocabulary word: node. A node is simply an individual computer or device within a network that accesses shared resources. So your smartphone, your laptop, even that wireless printer sitting in the corner, when they're on a network, those are all nodes. And honestly, this brilliantly illustrates that mistake we talked about right at the start. Let's examine this bus topology diagram to master this logical versus physical trap once and for all. Take a look at the red X on the left. It shows the visual arrangement, right? But just because those nodes are physically placed in a linear row, if they're connected via a central hub, that actually forms a star topology, not a bus. Now look over at the green check mark. This shows the actual operational logic, data traveling across a shared common backbone. You see, examiners aren't testing your interior design skills here. They are looking for the logical mechanism. They want you to explain exactly how the data travels across that shared medium, totally regardless of how the cables might look lying on the floor.
Let's see how this all builds when we introduce the actual hardware that connects these networks together. Here, we're comparing three absolutely crucial pieces of hardware: hubs, switches, and routers. The hub? That's your basic point-to-multipoint broadcaster. It blindly takes data and just shouts it to every single device, which, as you can imagine, can cause a massive broadcast storm and slow everything down to a crawl. Compare that to the switch, our intelligent segmenter. Notice that smart identification icon? A switch actually learns MAC addresses and sends data only to the specific device that needs it. It vastly improves efficiency. And then we have the router. That is your network gateway. It connects your local area network to the wide area network, aka the internet. To secure those top marks, you absolutely must compare these devices using these distinct operational mechanisms.
Now, if routers are the traffic directors, this next machine is the actual destination. Let's look at the powerhouse of the network, the server. Unpacking this visual, we can clearly see the exact three-step client-server cycle. Step 1, the client request. Step 2, server processing. And Step 3, the response. It's a really elegant, logical loop. But listen, here is exactly where you separate yourself from the average student. Avoid generic answers. Please don't just say the server does the work. If your exam scenario is about a busy office, you need to state that the file server processes the request and sends the specific document back to the client node. You've always got to anchor your answers with those specific scenario nouns. As our explainer expands from these local networks out into the vast, complex internet, the sheer volume of information can get a little overwhelming. That's exactly why I want you to memorize this 4-prompt reliability test. It's a super quick 4-step mental checklist. Whenever you're writing an answer about internet technologies, I want you to ask yourself, 1, what is it? 2, how does it work? 3, where is it used? And 4, why is it the best choice? Running your answers through this strict framework basically ensures you provide robust, full-mark responses every single time. Here is exactly how you apply that 4-prompt structure to World Wide Web and web browser questions. Success here means moving way beyond simple labels. You have to anchor your technical sequences directly to whatever scenario context they give you. So if the question asks how a browser displays a web page, you define the browser as software, explain the sequence of parsing HTML and rendering the page, connect it to the user's specific task, like, say, online shopping, and then explain the use of HTTPS for secure communication. The most common error students make here is just missing steps. Using a clear, logical sequence fixes that instantly. Of course, as we all know, the internet is not always a safe place. And mastering internet risks on your exam requires real precision. Look closely at the learner and connection section on the right. A massive pitfall for students is using vague wording when discussing threats. You absolutely must clearly contrast similar ideas. For instance, you need to articulate the distinct difference between malware, which is malicious software infecting a system, and social engineering, which instead relies on tricking human psychology. Just writing something like a hacker steals data is going to earn you 0 marks. No way around it. You have to specify the exact technical mechanism of the risk. From the web to the machine, embedded systems. All right, so we've scaled all the way up to global internet networks and cybersecurity. Now we are going to transition back down into highly specialized micro hardware. This is where code directly controls physical mechanisms in the real world. It's computing that you can literally touch and feel. Let's deconstruct this 3-layer learning cycle for embedded systems. You don't actually start with the code, you start with the application. Layer 1 is just simple language, like, what does the smart thermostat actually do? Then layer 2 shifts into technical vocabulary. We stop saying it reads the room and we start saying the sensor sends analog data to the microcontroller unit, which then triggers an actuator. Layer 3 is formatting that for the exam. But the absolute most vital part here is the context-specific specificity at the bottom. An industrial robotic arm uses completely different sensors and logic than a retail barcode scanner. Your explanation of the embedded system must strictly adhere to the exact industrial or retail scenario they give you. Now, all of these systems, from those massive servers down to the tiny embedded microcontrollers, are ultimately driven by algorithms. Let's pivot from hardware functionality into pure programming logic. Here's a really simple side-by-side comparison of how we write mathematical rounding. On the left, we see the standard pseudocode format, round, num, comma, 2. On the right, we see that exact same logic written in Visual Basic, math.round, num, comma, 2. Understanding how abstract logic translates into a specific programming language is a core competency you absolutely have to master. Let's dive deep into this visual worked example. We are rounding the decimal 1.438 to 2 decimal places. Step 1 is defining the input. Step 2 shows the result, 1.44. Why? Well, the logic is right there in the center. The third digit is 8, which is greater than or equal to 5, so normal mathematical rules dictate we round the 3 up to a 4. Pretty straightforward, right? But look at the exam strategy warning in the bottom right corner. When an exam uses command words like calculate or show, you cannot just write down 1.44. You must explicitly display these precise logical steps. You have to show you're working to earn full marks. You're basically proving to the examiner that you understand the process, not just the final answer. And just as we segmented physical networks earlier with our switches and routers, we have to segment our code using variable scope. Global variables are kind of like those network hubs. They broadcast their value everywhere and can be accessed from any routine in the program. Local variables, on the other hand, are highly specific. They are securely limited to the element where they're actually declared. This brilliantly reduces the risk of accidentally overwriting a value somewhere else in a complex program. Smartly utilizing local versus global variables isn't just good practice, it's exactly what examiners are testing for when they evaluate the efficiency and safety of your algorithms. Wow, we have covered immense ground today, from the volatility of primary memory through the logic of network topologies, all the way down into the precise syntax of programming.
I want to conclude this explainer with a provocative challenge for you to take into your next study session. In your next scenario answer, are you truly applying the 1 mark equals 1 distinct technical point rule? Or are you just repeating the exact same idea in slightly different words, kind of hoping for extra credit? Because understanding the true mechanism behind the technology is the only way to succeed. If this breakdown helped these concepts finally click into place for you, make sure to subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCS so you can absolutely excel in your Cambridge examinations. Let me know in the comments what you want to learn next. Stay focused, and I will see you in the next explainer.